Welcome to your next tutorial on recursion. Welcome to your next tutorial on recursion. Welcome to your next tutorial on recursion. And I'm wondering how many of you just got that horrible reference I was just making there. If you're understanding recursion. If you want another bad coder joke for recursion, just go to Google and search the word recursion. Maybe you'll get another little joke from there. So here we're stepping a little bit further into recursion. To start all the code for this actual tutorial, you can find under the usual comp1633 tutorial directory, tutorial 11. So again, before following along with this tutorial, I suggest you go copy that code and then come back and start. So I have a few questions here where once again we're doing a mix of doing some recursion with linked lists, and we're doing some recursion just normally working with non-linked lists, but like arrays or other things like that. We have, once again as always, our separate compilation setup where we have a make file to compile everything, this time to create the target for target 11. And you have just listing all the sources that need to be compiled and our general rules that you've always seen before that you can modify as we go. And again, my rule for these two tutorials in the make file is compiles, clears the screens, and runs it, just so that we have an ease of always going from compiling and actually running the program if we need to do multiple times. Within the file itself, you'll once again find the ioutil.h.cpp. These are those basic read functions that are used. You have list.cpp and list.h, which contain any code that relates to linked lists, so the recursive stuff for this lab. And then the rec.cpp and rec.h is any of the other methods that are recursive but are not dealing with linked lists. And then tutorial11.cpp contains the main. If you open up tutorial11.cpp, you'll see once again, just like tutorial 10, it actually sets up a basic menu, and each of the questions that requires running of the code and not tracing, you have as an individual actual function within here, and you have your basic main to read everything in based upon actual ints and run a menu for us and execute it and shut down the actual program. And just for the purpose to make this tutorial easier to run like last time, I have these pauses right here that you may not always have to have for your menu, but I'm just having here easier so you can see the output as we run. Otherwise, we can go first to question 1, the start of design for stuff for actual linked lists. So again, all the code for this can be found in the list.cpp file. You have the usual in here create demo that we've seen in previous labs, just to have a linked list that's set up that has numbers in it for you. For these demoing purposes, we have then the actual delete list just to deallocate all of it, and we have our usual write list to print it out so we can see it. So the first method here that you were supposed to design is using the normal node structure that we've seen before, is we want to write a recursive function definition for find target, which returns a pointer to the node containing the first occurrence of the given value, or null if it's not found. So this is assuming this is an integer array and we're searching for a match to this, and the idea is then this is the head, is the start of the list, and it is going to then return back the actual pointer to that node, but null if it's unable to find it. Now we can see the solution within here, and the normal thing to worry about again when you're doing recursive stuff is to think, what are your base cases? So what's the smallest if you were to subdivide the problem down? What are my base cases where I would stop actually doing the search itself? And then next is also then, okay, if you're not subdividing here, it's actually doing for the base cases. So if it's not the base cases, what is the recursive step where you're moving through it? Now you can see the solution here already, and I'll talk about it in a second, but what if we go back and actually just try to write a loop version of this, if you were to do it with a loop instead? Now most times these, like what we're doing here is these examples for recursion, you wouldn't have to do them in recursion if you can just do them in a loop. But why we start with this is kind of your training wheels of doing recursion, is that if you can envision how you would do in a loop, you can convert it over to how you would do in recursion to kind of get used to doing it until we get to more complex problems where recursion makes our lives easier. And that's generally we're going to have multiple recursive method actual calls. So this is kind of like, remember, your training wheels to work with this. So here is, I have the find target. Just going to call it actually loop right here so I can make sure everything compiles, blah, blah, blah. And so we want to go through and do our usual searching through the list. So first, as always, set up a reference that connects into the start of your actual list. Setting up the loop that will go through the entire list, so making sure this is cur doesn't equal null, so we go through every node and cur will fall off the end of the actual list, which is okay. And cur equals here at the bottom of the loop to actually get it so it's stepping the pointer forward through the entire list. And what I'm going to assume is that I'm just going to return cur, so if the list is empty, so head would be null, we won't go into this loop and return null, we expect. And if we go through this entire list and it doesn't find the actual data from right here, then we will exit out of the actual if it doesn't find the actual data, it'll exit out of the while loop, and cur will be null because it's gone off the end of the list, and so null will be returned. So saying fine here. So next what we do, and like this is your standard, like this setup here of this first chunk that I've got highlighted, this is your standard code for stepping through an entire list. And what you have to modify later on is, well, what are my stopping conditions and what happens to each node as I'm doing my work? Could modify it from there. So this is our find node. Next here, we're just setting if we find a match. So we're just seeing, okay, like if our current data is equal to target, then we found our match and we should actually stop. So we can modify our loop to exit properly. This time we'll do with a flag. And then we will say then, okay, if we find it here, boom. And we could modify then our loop. So I'm just using this Boolean variable here as what I call a flag, so that I can indicate when I change it to actually control exiting the actual loop itself. And then modifying here with an else is that so that it doesn't move the actual current. So we have it here going through. If it's not null or not at the end, right here, we'll go in. If the data matches, we'll say exits true, go down to loop, come back up here, it'll exit out and then return back the reference to the one we found. If the data doesn't actually match, it'll just move on to the very next one, and if we end up going off the end of the list, this right here will then control that we've hit the actual end. So that's the loop solution you'd be looking at. And so what you have to look for here is, where would you stop for this problem? Where's the smallest things and where would we stop when we're doing the search? And right here we know is, okay, one here is going to stop if cur becomes null. That's one case for exiting out. And the other is if cur equals to data. So there's your two base cases you're working with. And then the recursive step you're working with is this one right here, is where you're moving to the next node, because that's where we want. We want to move to the actual next node to do its work. And what we get is we know that the cur is being returned from right here. So on our base cases, we can just return these two values. And in our recurrent step, we keep track, okay, what was the return to us? We will return that back up and keep checking that data. So as we move through everything. So if you come down to here to the actual find target, you can see one base case, if the node coming is null, then the target we found is null, so it's being returned. Or if we have another base case, is if your data matches the target, then return this actual node. Otherwise, if we haven't hit any of these base cases, so we've ended the list or the actual target we found, then otherwise go on and then subdivide. So go to the next node and then see if it's the target, and then just assume what's coming back to me is the target that's been found by the sub work that's being done. So either it's gone all the way down to being null, or it's found the target, and then it'll return all the way back up into here, and then we finally return it to coming down there. So we can go and actually compile all this, make sure that first code I had worked. Ooh. That's exit, not end. Exit. There we go. So it did compile, We can then now right here run our find, and what you see here is this is the list and it's waiting for us to enter. So we have this list right here, 1 to 10, and then we can tell it what to enter. So we'll give it the target. We'll say that it's finding 7 here. Now it found it. So you can go through and trace this and add more of your prints to make sure that you're actually understanding this, and as you should go on to trace the actual data to make sure that you're getting it. But we have the case where it is running this that you're adding. You can see this in the run question 1 in the tut11.cpp. So you create me creating a list, writing it, reading in the actual int. If the int was read in properly here, then I call my find target on that list, getting the node, and it prints out if it does find it versus if it doesn't find it. So you can even see here where we run it again. I'll give it a value that's not in there, -1. Says it didn't find it. And say even if I go with 11, hey, not found. Now, I'll leave this to you guys so to practice with recursion, so I do highly suggest that you actually sit down and trace these through so you can work with this array and this array, the target, and I suggest you take the solution and you step through, make sure you're understanding exactly how it works. Now for question 3 here, it says, suppose the list is sorted in ascending order. Briefly describe how the solution will be changed to take advantage of this fact. And the one case for this is just the fact, the difference that we know sorted order and there's ordering, so we can slightly change our algorithm. If I switch over to OneNote, we can talk about that a little bit. If we know we had a list right here, just say like 1, 3, 6, 0, 2, just random integers for right here, and they're completely unordered. If I was searching for the actual number 2 within it, I have to go through each one. So I have to check the first one, then I have to check the next one, and so forth, and so forth, and so forth, till we find out it's actually in there. Right here. So we have to step through each one and completely stop. But what about the case of checking if something isn't in the actual list itself? So this was a 2. Is if I went with 5, is that I have to check the first one. No, doesn't match. Doesn't match, doesn't match, doesn't match, doesn't match, until we finally get down here to the end. And you're like, okay, we're at the end, so boom, it's not actually in the actual list. And so in the case for when we're doing the searches to find something, if it's not and doesn't end up being in there, we still have to go through all of these to search for them. But let's do this differently now. Let's go back to our case of where it's 2, and we're doing 2 and 5. But we'll go with a new list, but this time we assume it's actually a sorted list. So let's say 0, 2, 3, 7, 10. So that's our list now. So if we go with 2, it's the same thing. We have to go compare to the first one, doesn't match. We compare to the next one, it does match. Okay, so good. Then we go from right here. But now that we know this is ascending, we can stop and exit out. So we're good, we found that. But let's go with 5. Now normally, if we're doing the list before, we'd have to check through every single element all the way to the end to make sure it's not in that list. But now that we have 5, and we know that things are having to be sorted, we can check to the first one, okay, 0, doesn't match, okay, 2 doesn't match, 3 doesn't match, and here like 7 doesn't match, but wait, 7's larger than 5 right here. And you're like, okay, well, if we've already hit a number that's larger than what we're searching for, we don't need to search through the rest of those. We don't need to search through the rest of the list. We can actually just stop. And so as we're going through, we can stop when we're at the end of the list if we actually need to. So if it was something that was larger than everything that was actually in the list. But we can also stop the actual searching earlier if we find another base case where, oh, the next one's bigger than what we're looking for, then just stop. And so this just more makes the algorithm a little bit more efficient. So let's switch back to the actual code. And you can see that then down below. So we got find target, then I've got find target sorted, and you can see that it adds it in, that we still have the same base case then of if it's equal to null. We then have one if we found the target, but we have a new base case we can take advantage of is if our data is larger than the target, then stop. And so this is just going to make it more efficient for stuff. And it's a similar thing that we could add this into the actual loop itself to stop. So this means it stops searching, and so if it found out by the 6th element of a 1,000 element array that, oh, the rest of the data is larger, it just stops. So it'll make your algorithm more efficient. But otherwise, everything else is exactly the same. And if you run the code, you can see where it's being actually called when we search for anything from right here. So say like boom, search for 3 here. You can see that I am calling that found sorted. So you can go through tracing that yourself. And I do suggest if you're not sure exactly how this is working, go through with the example and trace it yourself. It's good practice. Okay, on to the next question, making sure this tutorial doesn't get too long. Now, this next question here is one that you guys will have to work on yourself to hand in. I'm not going to code it here. I'm going to talk about how you're going to do it, but I'm going to leave the challenge for you to finalize the coding of this. So all of the work for this has got to be done in the rec.cpp. So you can open that now. And you'll see you got the method indexMax. And so you also have question 4 in tut11.cpp. You can see where it's actually called. So this is in run question 4. It'll go through. Now what this method needs to do is write a recursive definition for the index of max, which takes an array of numbers and returns the index of the maximum value. You may assume that the array contains one or more numbers that's actually within it. Note, for this problem, the function receives only one subscript, the index of the last value in the array, thus the array is fully from 0 up to high. So this high is really like, if we've got an array, this is up to the highest index it actually needs to search to do its actual work, right here. Now, realize the challenge I would accept here is like, okay, this is just index. You're just trying to find the largest actual number. So before going into any of the rest of the code, if I come back here to OneNote, we just assume you have the array coming in. So we'll draw an array right here. And so you've got the array, the numbers above each box is the actual index number from right here, and we'll assume that we have, say, a high value of 4, seeing that's what's filled in here. So we'll assume that we then have some data, right here, where you could have repeating numbers that are coming into this. And so what you have coming in the array is that the high value h says to the actual index that has the highest value of what's stored in here. So there could still be more space in the rest of the array right here afterwards, but it's not being used. So your function just has to search from index 0 up to and including index high to search for which is the actual largest value. And you know here, this is your usual one where you're looking through, you look at the first one, okay, I've got 3, so 3 is the biggest I've seen so far. Then I go to -1. Is -1 bigger than -3? No. So we just move on to the next one. Same thing. Is 2 bigger than 3? No. Then we have right here is, okay, 5 is bigger than 3, so 5 is the actual new largest. And then you go to the last part right here and say, okay, 1, is that actually larger or not? Nope, it isn't. So 5 is the largest number you have. Now this method is supposed to return back the index of the max. So we found that 5 was here, but you actually have 3 is the index where 5 number is located, so we have to return back the 3. So if we were to go back and do this again, we'd have to keep track of the indexes where we've seen things. So you start in the beginning, and you're like, okay, largest number I've seen is 3, the index where it is 7, so index value. Same thing, you go through, and you're like, okay, -1, okay, not bigger than 3. You get 2, it's not bigger than 3. We get 5, that is bigger than 3. So we got 5 here, and it's at index 3. And so we keep going forwards. You got 1 right here. 1's not bigger, so nothing else. We've hit high, so we stop, and we see that 3 should be the index that we actually have to return. That's how you have to solve the actual problem. So what I suggest for you to do here is, first, how would you write this as a loop? Just write it as a loop. You can even get in here that it's not actually recursive. So you go back, and what I suggest first off is just write this as it's a loop. So if you were doing this and you were given this is a problem, just how would I search through the array using just a loop to solve this problem and get it to actually run in the main and see if you got everything working properly from this. After that, you think like those previous steps. Since we're just converting a loop over, you're first looking at, okay, well, what are the stopping conditions that would stop the loop? So, we've hit the high, or we've hit that thing that we've actually found, and then you would return back that either like, oh, I haven't found it, or I have actually found the actual value that's coming back from right here. So where you actually find the highest value, because there will be a highest value throughout all of this. So you need to set up, so how would I do this as a loop to do it? So working with an array that at least has one or more values. And the next thing, okay, well, how would I stop doing this and how would I recurse? And that you're stepping forwards, remember it's the indexes that you're stepping for. There's a good actual hint. You have the high that you're passing through, but you have right here is like, well, what's the index that I'm searching up to? So, I could be searching to the end. So I could start at the end, work my way backwards, maybe counting backwards from what is high, potentially. So try to work it out that way with the index and seeing how you would solve this. So this is again for marks. So you have to complete the index of max and it's got to work properly. So make sure, do not just code it, but go and look at that question for the main. Make sure that the main is working properly and don't modify the main to make your code work. You just have this one function call that you have to do and make sure that you're getting this to work properly. So it's the one time where I'm not going to direct you through it, but I've given you some hints and I'll give a challenge for you to write this for actual submission. Okay, the next method here is writing a recursive function which will determine whether two linked lists are equal or not. Now remember for this is that we have done in one of the previous linked list tutorials, i.e. more linked lists, there was an equals list actual method that was provided that did that with an actual loop. So I suggest you go take a look back at that and then compare to the actual recursive code that you will see here, which is in list.cpp. You can see this with the equals list, where it has a base case. If the heads are both null, return true that they're the same. If head 2 is equal to null, but then if head 1 is equal to null, but the other one, so they're not both equally from right here, because if they're both, they'd go into here, but if we come after that one of them's null and the other one isn't from right here, then it's false, they're not the same. If we come in and the data doesn't match, then they're not the same. Otherwise, then step to the next one. So matching anything from there. So it's a quicker one here, but I do suggest you spend the time to go back to understand what's happened between these two methods. Question 6 here is then just dealing with another kind of recursive problem of n choose r. So you can find this one in rec.cpp. And this is provided with a solution as well. And so from right here is that denotes all ways of choosing R elements from a set of N elements without considering the order of the choices. So where N is equal to R. And so this is more, there's an actual formula for this if you want to go look it up. It's just N choose R. This is a mathematical thing. This is a reoccurrence formula that you could actually get. And it's a quick conversion over to the actual recursion. And so if you want to look it up, again, just go Google or search for the N choose R and look for the reoccurrence. And you can see how it's written and you can see the base cases of what happens between these two. But this is the one case now where we're getting two recursive calls for a step. So to go in the previous steps going back. So the N minus 1, right here, R minus 1 to N minus 1 and R are the choices. So I suggest you practice with this one. Go take a look at that function and actually breaking it down. Now the last one is a little bit larger of an actual method. So this is going to be working with linked lists again. So in list.cpp. And you have merge. Now here is write a recursive merge function which takes two sorted lists and builds one sorted list containing all of the values from the original. The input list will not remain intact during this merge, so i.e. both inputs will be empty upon the return. So what you'll get is head 1 and head 2, those lists will be empty coming back out, and all will be merged into a new list that's coming here. So for this one again, I'm not going to go through every step from this, but I want you to take this as a challenge to code this. So first, try coding this non-recursively. How would you just do this with loops? And then take your loop solution and convert that over to a recursive solution. And a hint here is to think the different cases you could have for the list and take advantage of the stuff that you know the lists are actually sorted. And you want to go through the different combinations that you have. So if I switch over to OneNote, let's see if I can, off the top of my head, think of some of those actual combinations. And you want to think of where it would branch out for the lists. So you know I'm going to have list 1, and I'm going to have list 2, and I have to go through different combinations of what could be happening. And here what could be happening is we're just merging everything in the list, but it's going to be more affected this time by the actual size of the actual list right here. So let's see, you could have one case, 1, 2, 3. So these are valid. They're two sorted lists, you can see coming right here, but what's important is each one just has 3 elements right here. And so if I was to start doing this, these are equal. So this is just one case, you have to worry about it. And if I was to merge these, the merged list is supposed to look like then, okay, well I would have 1, 1, 2, 3, 4 to be ascending. It's the 1 from there, the 1 from there, then the 2, then the 3, and I even noticed that I missed a 3. So then I would have a 3 and then a 4. So that 3, that 4. So I can all pull them out. Now that's the resulting list we're supposed to get. But what I would start is we have 2 lists, so you know I would set a reference to the very beginning of each of these. So current 1, current 2 that we're working with, and we want to look with both and see, well, which one has the smallest, because they're supposed to be ascending. So we know we always want to take the smallest from each list. And we can always just default, if they're the same, just take from list 1. We're going right here. So we'll just assume again, if the 2 values are the same between these two, what's being referenced, we'll just remove the one that's from list 1. And what we're doing is we're adding it to list 2. So we're starting that each time. So list 2 starts out being null. We're looking here as like, okay, the first list, it's got a 1 in there. So we take that out, we add it down here. We then move that first reference to the next one. Then we start comparing 2 to 1. Okay, list 2's got the correct one. Right there. And then this one moves forward. And we keep going through the same process. 2 compared to 3. Okay, the 2 gets removed. This one moves over. There we have 3 to 3. So we take this out of the list. This one then becomes null. Come right here. And now that we removed all the rest of these, we don't need to do anything else. We just copy the rest of these coming out. So you can see how I was stepping forwards, and now I'm hitting a case where one of these ends up being null. I can just copy the rest from the rest of the other list. So you have that cases. So there is a case here is like, oh, I've copied all the stuff out of this list, so I keep comparing, and I'm doing that up until this point for the actual comparisons, but then this one's empty. Then I have some different code as well. Once one is empty, I just copy the rest of these actually out. And we get in our entire list. So you've got that one case where I would say you want to worry about these different ones and where it's copying from. So you could get where they're the same size of actual lists, but if we exhaust everything in this list, so list 1, we need to copy everything else from list 2. And the reverse could happen. If we exhaust taking everything out of list 2, we need to copy out everything else that's in list 1. And so you could get all those cases. And you could get, again, that the size of the list equals this size of the list. The size of the list over here is less than this size of the list. Or this size of the list is larger than this size of the list. Or they're just like empty from right here. So you have all those cases of where you can copy from like different parts of the lists over. And where you may have cases where, hey, you hit the end of one list. You need to copy the rest of what's coming out. So I do, again, so go and write this as a normal loop. One, it's very good practice for working with the linked list itself for doing the actual merge. And then come back and write the recursive. So you do have a solution here for the recursive, so you could reverse engineer this to figure out the actual normal one of what's happening here. But I suggest you work on both, understand, well, how are we doing this with the loop, and then come back to this one and see how is this recursive one working, matching up to what you're getting. And so, you know, things of like, oh, the lists are both are empty, return back here. If the list of head 1 is null, you're in, then look here. The rest of R2 equals the rest of what you're pulling here. Oh, look, head 2 is empty. So one list is empty, we're giving a node back here. One other list is empty, we're giving a node back here. Otherwise, we are checking and comparing the data and knowing where we list from right here and doing the recursion and doing that same thing that we linked the lists up in the end, which one we step forwards from. So shifting those heads forward. So if you're not sure about any of this, take a small example, like what you're seeing in the code above, and then actually trace it through the recursion. Try to write this as your loop one, and then go back to write your own recursive version. Okay. So that's a lot of me talking right there. That's about 30 minutes for this tutorial. Gives you some more time to sit down and keep working on that first actual activity. So this one's not due, but it's very good practice because it's a harder thing that you could see on a future test or something like that and give you practice for future recursive assignments and working with linked lists. But just remember that you have to complete and actually solve the actual find max. So again, I suggest step one, write it as a loop solution, get that working, and then step 2, convert your loop solution over to a recursive version if you need those steps. Okay. If you're doing the rest of the code, you'll see as usual within the actual main that there are, again, your functions. So printing everything out here for the same, so question 5. For like the equals lists, you have question 6 then for the n choose r, and you have question 7 for actually doing the merges of the actual lists. So we can show, at least I should demo live, showing the equals list. You can see the comparisons of being true or false, which ones are the same or shouldn't be. It's fine. And you have 6 right here, say true. 4, choose 2, see the rest of the combinations to test, and finally that actual merge that you can get working. As you can see, we have these two lists and then the proper merge list that's coming out of this, and that these two should be null in the actual and the after the case once these two have been merged in. And so again, go on right through this, get your extra practice, and continue being the awesome people that I know all of you are.